Hello, welcome to M4.2, the second module in Unit 4. This module covers the absorption and reflection of light. In the last module, we talked about light as an electromagnetic wave with all of the familiar wave properties, such as the frequency, the wavelength, etc., and how it oscillates through space and propagates at the speed of light. Most sources of light produce light waves over a fairly large area, and the light produced has many different wavelengths. So you can see that here this flashlight is depicted as producing red, yellow, green, there's some blue in there, and some violet. And that's because this flashlight is actually producing a huge mixture of wavelengths, all the wavelengths that you can see all at once. The sun also produces a whole bunch of wavelengths, although of course in this picture it's not showing it. So there are three types of light. We have what's called white light, which is a mixture of many different wavelengths. In fact, properly speaking, white light is a mixture of every single wavelength in equal intensity. But in practice, really, if we have any combination of many different wavelengths so that it's approximately even across the board, we call that white light. Another word that we have for it is polychromatic light. And polychromatic just means poly, which is many, and chromatic, which is colors. So it has many different wavelengths. It is polychromatic. We can also have monochromatic light sources, which are a light source that produces only a single wavelength of light. Now, you may notice in here that even though all the waves are depicted as being the same wavelength, the same color green, you'll notice that the peak here is not in the same place as this peak here, and this peak here is not lined up with this peak here. So these waves are not in phase. And of course, the polychromatic light is also not going to be in phase. In fact, it can't be in phase since it has different wavelengths. You'll never be able to line up every single wavelength in polychromatic light. So that brings me to the third type of light, which is monochromatic light. But it is also coherent. And by coherent, we mean that all of the waves that are being emitted are in phase. So you can see that all of the peaks line up, all of the troughs line up, everything lines up, so it's emitting only a single wavelength, and it is emitting all of its light rays coherently, meaning in phase. And most lasers are coherent light sources. Most of the sources of light that we have are white light sources. They emit polychromatic light that is not in phase. So that is what we have to deal with most of the time. Occasionally, to make problems easier, I'll go ahead and say that it's a monochromatic light source. And if it's a monochromatic light source, that makes things easier because you only have to deal with a single wavelength or a single frequency. Often when we deal with light, it's really cumbersome to deal with those oscillations. But luckily, the oscillations of visible light, their wavelengths are on the nanometer scale, whereas the objects that we're looking at are much bigger than nanometers. So these nanometer length oscillations can actually just be averaged out. So we take an average intensity, an average energy, and we model each wave as just a straight ray of light. So when I say ray, I am modeling an electromagnetic wave as just one of these straight arrows. Oops, I can't draw very straight, but it's one of those straight arrows. And then if I talk about a beam of light, I'm usually talking about a collection of rays. And the same thing can be said for the flashlight. So all of these rays are traveling through space, and they're traveling through space at a speed or a velocity. It's your propagation velocity of light, which, as we said in the last lecture, is equal to this number c, which is equal to 3 times 10 to the 8th meters per second. So all light will travel in a straight line at 3 times 10 to the 8th meters per second until something happens to either change its course or to stop it. One of the things that can stop it is absorption. Absorption happens when light hits a molecule or an atom of some material. Now, atoms and molecules contain electrons. As we know, the electrons kind of circle around the atom. If you know your chemistry, you know that actually it's more like kind of a cloudy existence for the electron. But we can model it as an electron circling in an orbit around the atom. And each of these orbits represents an energy level. So in order to increase or decrease in energy, the electron must jump from one orbit to the other. So if we say that this ground state orbit has an energy of E1, that means the electron in that orbit has an energy of E1. And if we want this electron to jump to the outer orbit, which has energy E2, it needs to gain an energy that makes up for the difference between these two energy levels. So we'll call that delta E, or the change in energy. So for the electron to jump from one orbit to another within the atom, it has to get this energy from somewhere. And it's going to get the energy from this photon here. Now we said in the last lecture that that light can be either a wave or it can act as a particle, which is a photon. So when light travels through space, it acts as a wave, but when it interacts with the electron, it acts as a particle. Now remember the gamma symbol here, it's a Greek gamma, and that is the symbol for a photon. So it's going to interact with this electron as a photon, which means that its energy is going to be hf, where h is that constant, Planck's constant. So in order for this electron to jump up to the next energy level, it needs to absorb exactly the right energy from the photon, which is going to be our delta E. Now we also know that the propagation speed, which is c, is equal to the wavelength times the frequency. So what we really want to know is the wavelength of the light that's going to be absorbed. So we can solve for it by putting hc over the change in energy, and that'll give us the wavelength that's absorbed. And it turns out that hc is a nice even number. It's approximately 2 times 10 to the negative 16th joules per nanometer. So in this example, I've used the energy levels for hydrogen. The difference of energy levels for hydrogen between the ground state and the second state is just 1.6 times 10 to the 18th joules. So if we want to find the lambda absorbed, we want to find the wavelength that's going to be absorbed by an electron that goes from the ground state to the next state of the hydrogen atom, we take this hc, we divide it by the amount of energy that the electron needs to absorb. You can see that our joules cancel. And we end up with 1.25 times 10 to the 2 nanometers, or 125 nanometers. So that means that light that is absorbed by the hydrogen atom that successfully gets this electron from the first level to the second level has to be 125 nanometers in wavelength, which is not actually a visible color to us. This is in the ultraviolet spectrum. But many other molecules do have wavelengths in the visible spectrum that they can absorb in order to jump to a higher energy level. So what we have here is we have a red shirt and blue shorts. But the reason that the shirt looks red and that the short looks blue is that this red shirt is actually absorbing many different wavelengths. This red shirt is actually absorbing all of these wavelengths, or at least enough of them that they don't show up, so that the red shirt only shows these red wavelengths. The shorts, on the other hand, are absorbing all of the red and the yellow, all of the longer wavelengths. And the only wavelength that is not absorbed is this blue. So that's what makes the shirt look red and the shorts look blue. Of course, the red shirt and the blue shorts are not actually producing the light that is absorbed, and they're not producing the red and blue rays that aren't absorbed and that eventually reach our eyes. There is some source of light somewhere else, and the light is coming down, reaching the shirt, some of it's getting absorbed, and then the red rays bounce off of the shirt. And this bouncing off of the shirt is called reflection. So next we're going to talk about reflection, which is another way that we can change the trajectory of white light. We said that white light travels in a straight line at the speed of light. If it is reflected, we can change this direction. So reflection is pretty straightforward. It's a concept that we see every day, so hopefully most of you don't have too difficult of a time with it. But let's talk about a little bit of the terminology. When the ray comes in towards the object that it's going to reflect off of, it is called the incident ray. So this ray here is an incident ray. And then once it bounces off and turns around, it's called the reflected ray. Now, if the incident ray comes in 90 degrees to the surface, then it's going to bounce back and go in exactly the same direction. However, the light doesn't always come in exactly 90 degrees. So now we have an incident ray that is coming in at an angle. So when it comes in at an angle, I'll make this theta 1. It's going to bounce back off of the surface, and this is a really easy equation because it's going to bounce off at exactly the same angle as it came in at. And this angle is measured from this normal line right here. So there's that normal line again. We've seen normal lines quite a bit. The normal line is perpendicular to the surface. So that's where we measure theta 1 and theta 2. So this law of reflection is pretty easy. The incident angle is equal to the reflected angle. But it's important that you get accustomed to the language that I'm using, the way that I'm saying incident ray and reflected ray, and it's very important that you understand the normal line, because when we move on to another concept called refraction, you're really going to need to make sure that you draw your normal line correctly so that you get the correct answers for your angles. So to emphasize, the law of reflection is just that the angle of incidence is equal to the angle of reflection. Okay, so what if the surface that it's reflecting off of is not flat? Well, it can still bounce off of a curved surface as well. And the law of reflection still applies, and the law of reflection doesn't change. Theta 1 still equals theta 2. And they are still measured from this normal line here. But the normal line, it can't be 90 degrees to a curved surface, so it's 90 degrees to a tangent line that is tangent to the surface at the point that the ray hits. So you draw a tangent line right at that point, 90 degrees to that is your normal line, and then that's how you measure your theta 1 and your theta 2. So if you have a bunch of rays that are all coming in and they're all bouncing off of this surface, if they come in parallel, and the surface is smooth, meaning that there aren't any curves, there aren't any bumps, then all of these angles are going to end up being the same. And all of the reflected angles are going to be the same also. So your rays coming out are also going to be parallel. So when this happens, any information that is being transmitted in these waves is also reflected perfectly orderly fashion in the reflected waves. So what this means is that you will get a nice, smooth, clear reflection. On the other hand, if you have a bunch of rays come in and you've got a really bumpy surface, then the normal line to each surface is going to be at a different angle. So you can see I'm drawing the different normal lines, or the different tangents to the surface, or I'm trying to at least. And that means the normal lines are all going to be different. So all of these angles are going to be different, and the rays are going to scatter in every direction. So when light comes in and bounces off of a curved surface, it's not that the light doesn't reflect. The light still reflects, but it doesn't reflect in an orderly fashion, so the information carried by the light is going to be all scrambled up, and you're not going to get a nice clear reflection. So you may think about in regular life how you look in a mirror and you see a nice, clear, perfect reflection of yourself. But if you look in maybe the shiny surface of a car, you can see yourself, but there's a little bit of distortion. It's not really super clear. And then you can take maybe some other surface like a table, and you look at it and you're not going to see your reflection at all. Now that doesn't mean that light rays aren't bouncing off of the table and reaching your eyes. It does. It just means that light rays aren't bouncing off in an organized fashion so that you can't see reflections of other things on the table. So, for example, the beam of rays that are bouncing off of the red shirt in the previous slides will be all scattered all over the place. So that's why you can't see your reflection in a red t-shirt. And a word for scattered light like this, the proper physics word, is diffuse. So scattered light creates a diffuse reflection. Okay, so now that we've had light created and we've had light reflecting or being absorbed, the next thing we want to do is we want to detect the light somehow. So usually when we think about detecting light, we think about the human eye because vision is so important to us that we all think about, well, what can we see? How do we see it? So we're going to talk a little bit more about how the eye works later, but we need a little bit more information about lenses before we do that. But for now, we're just going to talk about how the light actually reaches the eye to be detected. So in addition to the eye, other things can detect light. We have cameras, which you're all familiar with, cell phone cameras. Solar panels are actually detecting electromagnetic radiation. This thing here is a motion sensor. So motion sensors are just detecting changes in the light that they're seeing. This is one of those night lights that automatically turns on when the light reaches a certain low level. So all of these things are actually detecting light, and they all detect light after it has bounced off in a certain way. We can also detect light that's not in the visible spectrum. So this right here is an infrared, a picture of a dog that was taken with an infrared camera. This right here was taken by an X-ray detector, and it is actually our sun. And this here is some fruit that was taken with an ultraviolet camera or an ultraviolet sensor. Now, of course, these pictures that we're looking at are in visible light, and that's because we couldn't show you a picture of an infrared dog or an ultraviolet piece of fruit because you wouldn't be able to see them. You can't see the infrared light or the ultraviolet. That's why dogs don't look like that and fruit doesn't look like that. So in all of these pictures where they say that this was taken with an X-ray camera or an ultraviolet camera, it means that they're detecting these non-visible electromagnetic waves, but then we're translating it into some sort of visible color scheme so that we can show you these pretty and very cool pictures of the dog and whatever else you might want to see in non-visible rays of light. Okay, so we can now start really talking about optics. This is the study of sight and the behavior of light in very, very simple terms. So light is produced as electromagnetic radiation at some source. So here the sun is our source, and it is producing electromagnetic radiation. Those light waves travel all the way to Earth, and then they're going to hit the object, which in this case is, of course, a beagle. So they hit the object. Some of it's going to get absorbed, but some of it is also going to get reflected. Some of that reflected light goes this way, and then it's going to hit the sensor, which in this case is our eyes. So the very basic picture of optics, the basic phenomenon that we're going to look like, is light that goes from a source to an object to some sort of sensor. Now, of course, in reality, the situation is a lot more complicated. For example, we know that the sun is emitting Many, 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 many rays. Lots of rays, and it's emitting them in all different directions. And we know that some of those rays are going to hit the dog and be absorbed. So hit the dog and it's absorbed. Hit the dog and it's going to be absorbed. And some of them are going to be reflected, but they're going to reflect off into some other direction. It takes a very particular situation for a light wave to be emitted by a source, hit the object, and reflect back at exactly the right angle to reach the source. So we're actually awash in electromagnetic radiation all around us, and we're just going to choose to study the one lucky ray that comes off of the source, hits the dog, and then or the object, and then comes back to our eye. So this is the simple picture of just that one ray. It hits the dog, it comes back to our eye, and that is the one picture that we're going to study. We're going to study the angle at which the light comes in, oops, which is called the incident ray. And then we're going to look at the reflected ray. And remember, the angle between them is very important, and especially for a reflected ray, the incident angle is always equal to the angle of reflection. So mirrors are another simple picture that we can draw, and it actually involves one more bounce than what we looked at before. So when you do mirror images, when you're looking at problems with mirrors, we usually don't bother to draw a source, but there's always a source in there. So somewhere, these rays are coming from somewhere. The ray hits the guy's head, bounces off at a particular angle, which you can see this green line here, bounces off at a particular angle where it goes from the head to the point on the mirror, and then it bounces off the mirror and goes back to the person's eyes. So every time you look in a mirror and you see an image in a mirror, that light ray has traveled from a source. It has hit whatever you're looking at in the mirror, it bounces off the mirror, and then it comes back to your eye. And you can see that down here, this particular light ray came from some source, we don't know what, maybe it's the bathroom light over here, bounced off of his shoe, bounced off at just the right angle to hit the mirror, and it hit the mirror right at this particular point, so that the angle of incidence and the angle of reflection put that ray right back in your eye so that you can actually see this guy's foot. So in reality, every single piece of that image that he sees is another set of these light rays bouncing off. So here at his knee, there's some other ray that's coming off like this. Oops. Coming off and ending up at his eye. And his waist here is another ray. I'm sorry, that wouldn't hit at the same point. Let me redraw that. That would hit more like that and hit his eye. His waist would hit like this and go back to his eye. His belt would hit somewhere around here and go back to his eye. His tie will hit somewhere around here. So every single part of his body is actually a ray that is bouncing from the source, off of whatever you're seeing, onto the mirror, and then back in your eye. So lots of bouncing around by the time it gets to your eye. Okay, but the man's brain doesn't see all of that. In fact, the man's brain doesn't even see it bouncing off of the mirror. The man's brain interprets the light as though the light traveled in a straight line from his head or from his shoes to his eyes. So his brain will recreate the image as if the mirror wasn't there. His brain thinks that the light source was just right here and that it just did one bounce and bounced straight to his eyes like that. That's what his brain interprets this light to mean, even though it actually bounced off of the mirror. And similarly for his shoe, his brain interprets the light as bouncing off the shoe and in a straight line directly to his eye. So his brain forms this image in the mirror that you may be familiar with, and this image is called a virtual image because it's an image that we see in the mirror, but the guy is not actually standing behind the mirror, and the light rays that he's seeing never actually traveled behind the mirror. So he sees this virtual image. All right, so we're going to talk a whole lot more about rays, but that is how absorption and reflection works. We talked about how optics studies the processes in which light is produced, reflected, or absorbed from surfaces, and then it's detected by eyes or devices. We talked about how light can be modeled as rays that travel in a straight line, and they travel, of course, at this speed, which I'm going to keep writing because it's really important. C equals 3 times 10 to the 8th meters per second is the speed of light. So light can be absorbed or reflected by surfaces and substances. The way that it's absorbed is by atoms and molecules in little chunks that correspond to a certain energy. So that means that certain materials can absorb only certain wavelengths of light. The law of reflection states that the angle of incidence is always equal to the angle of reflection as measured from a normal that is drawn to the reflecting surface. And if the reflecting surface is curved, remember we need to draw that normal to the tangent. A smooth surface results in a clear reflection of light, and a rough surface results in scattered light and a blurry or diffuse reflection. And then a flat mirror is one of the simplest examples of light reflecting off of something to form an image. So that's all I'm going to talk about in this module. I had a very frustrating morning, so hopefully my narration wasn't too hard for you to follow. Next module, we're going to talk about one more important thing that light can do other than absorbing and reflecting. It can also be refracted, and that's where a lot of students have difficulty. Reflection is pretty simple. We see it in mirrors every day. We have a good conceptual grasp of it, but refraction is a little bit harder. So we're going to spend the next module on that.